Before we move on, we should really take a break here and prove the second part of the fundamental theorem. That's something that we haven't even used yet, but we will be using a lot. So let's take a look at it. The second part of the fundamental theorem of calculus says if little f is continuous on the interval of x values between a and b, and if f prime is equal to little f, what that actually means is f, big F, is the antiderivative of little f. Then we'll have to show the results of the fundamental theorem. That means that the integral from a to b of f, little f of x dx is equal to capital F of b minus capital F of a. What does that say? It says the integral from a to b of f of x dx is equal to the antiderivative of little f evaluated at the upper limit minus the antiderivative of little f evaluated at the lower limit. Oh, this is going to be very powerful. Let's see if we can prove it. Well, first let's name things. Let's let g of x equal the integral from a to x f of t dt. Then the fundamental theorem part 1 says that g prime of x would be equal to little f of x. In other words, g is an antiderivative of the function f. Now I say an because you know these things are not going to be unique. You can always add a constant c and come up with another version of the antiderivative. Okay, let capital F be another antiderivative of little f on the same interval. Okay, so we've got two of them. We've got g and we've got capital F. If it's true that capital F is an antiderivative, it means that f prime of x is the same as g prime of x for all x's on the open interval from a to b. Thus, by note 75, go back and look up note 75, that means that capital F evaluated at x minus g evaluated at x equals a constant. Remember, note 75 says if you have derivatives equal, the original functions differ only by a constant. In other words, capital F of x is equal to little g of x plus c for a less than x less than b. I'll put a star there because we're going to refer back to that. Now, capital F is differentiable on AB. How do I know that capital F is differentiable? Because we made an assumption at the beginning that capital F prime is equal to little f. That means capital F prime exists. The derivative exists means that aren't things differentiable. Thus, by note 41, go back and look at note 41, we know that F differentiable means that implies, not equals, but implies that f is continuous on the same interval. Therefore, since capital F is continuous, by the definition of continuity, the limit as x approaches some number, let's say a of capital F of x is equal to f of b, and another limit as x approaches another number, b of capital F of x is equal to f of b. Both of those statements are true by the definition of continuity. And we can make a similar statement about the other function. G is differentiable. That's given. That implies that G is continuous. Now, if it's continuous, that means that, and of course, C, a constant, is going to be continuous because numbers like y equals c, the constant function, is always going to be continuous. So we can make the following statement. The limit as x approaches some number, let's say a, of g of x plus c, that's the sum of two continuous functions. It equals g of a plus c. And the limit as x approaches b of g of x plus c is equal to g of b plus c. And that, again, is by the definition of continuity. Therefore, we may take the difference of these limits and go back to the star equation. We get f of b equals g of b plus c, and subtract capital F of a equals g of a plus c. And that will give us, on the left, it gives us f of b minus f of a. On the right, it gives us g of b minus g of a because the c's cancel. Well, let's continue working on the right. What is g of b? Well, it's the integral from a to b of f of t dt, because that's the way it was defined, and minus the integral from a to a. Why is that? Why is the upper limit a? Because g of x was equal to the integral from a to x, so g of a is equal to the integral from a to a of f of t dt. Well, you know, we have a rule in the properties of definite integrals that says if your lower limit and your upper limit match, then the integral is going to be 0. So that entire integral will disappear. But the whole statement on that line is true by the fundamental theorem part 1. And since the second term went to 0, we have this expression equal to just the integral from a to b, f of t dt. So what have we shown here at the bottom? We've shown that capital F of b minus capital F of a is equal to the integral from a to b of little f of t dt, which is exactly what we were trying to prove. Quod erratus demonstrandum. We're finished. Oh, by the way, don't worry about the fact that we have t's on the right side of our final statement instead of x's, because those are just dummy variables. I don't care what letter you use. It still says what we're trying to show at the very beginning.